In this video I will explain the demo setup, so you can see how you can create sophisticated AI, even though the demo setup itself is still at a basic level. It is recommended to watch the previous videos about the graph editor basics, as well as the purpose of the different node setting types. It is also helpful to look into the control panel video. So you have a basic understanding what components are needed for the game environment in combination with the node settings in your graph editor. Alright, let's first establish the body we want to use. For this example, we will take the default AiMalgam model called Malgi and assign every required component from scratch, so no predefined prefab is used in this example. By default, a rigged and animated model has an animator already assigned. We will need that later. And we can already set up the controller we will need. The most crucial part is to add the AiMalgam entity component. And let's add a decision system as well. Let's choose the update one, because if we choose the no loop one, some other mono behavior needs to call the tick method in order for it to work. Alright. Can press the autofill button and it will find the AiMalgam entity, and now we are missing a node graph. Let's create one. We will add a single decider as the root. In this case, because it is a very simple setup, a multiple decider would work as well, but if you want to add further logic for this AI tree, the multiple decider would just apply it as well without any branching or exclusion. So we prepared with a single decider. And then to add multiple actions, we add a multiple decider as its first child, or it should be the second one, because the first one could be something like death animation or so, which is then or should be dominant or the first chosen one. Alright, let's set the child decider as a leaf, so it will support action settings. Now what do we want? We want movement and movement animation. So we will add follow settings to follow the companion, and it should also repeat forever. And we want to add animation settings to display the right movement animation. For the follow settings, we want to we want to flank the target to always be at a certain angle to it. Let's say slightly behind it and at a distance between 2 and 3 units. The flank should be static and don't refresh. We want to cache the target. Can output the resulting target if you want, and of course if it is set up in the engine. For now we don't want any filter, but it might be useful later if we want to differentiate between enemies and companions or neutral ones. We want to add entities to follow. We could also do it locally, but I think it's cleaner this way. Well, although for this small example it's not cleaner, but we can reuse it then in other scenes, not to make a hard reference every time. So this is set up. We need to set up targeting. Do we have already an existing one? Let's take the first found companion, not by distance. Always stick loyal to the first found. That's why we also enable caching. And that's basically it for the follow settings. Let's take a look at the animator settings. We choose the humanoid controller because we use a humanoid entity. If it would be a spider or a dog or something, you would have the respective animation controller for it as well, so it's not restricted to any model or animation. We use the blend move. Also, we want to read the current movement from the navmesh agent. So we set this up, read it from the blackboard, and it's a float value. And let's define the same name. I think that should be it as well. Yeah, clamping sounds about right. Or maybe mapping as well. Well, I don't know the input values, so let's stick with that setup. Quite simple. We can close it. And now we need to tell the runtime set that we want to register this entity to it, so that the follow... no, it's not this one. We want a companion, so let's create a companion first. Companion, or it's the other way around. This is the target and this is the companion. Also, let's unpack it so it doesn't annoy us. Right. Since we need to target it, let's add an AiMalgam entity. Fill it up. Set the newly created runtime set. Let's rename everything. Companion runtime set, so we don't get confused. Alright, now we have set up the target, and we could theoretically, instead of using the runtime set, assign it directly in the destination container, but for that we first need to create the engine. If you're not sure what engines you need, just assign the graph first and then click the refresh required engines button. You'll see we need a follow and animator engine if you expand the engines list. Only then will the graph work and not throw any errors. Set the animator engine. Can use an update engine. Autofill, which will also set the animator. We want to listen to any state changes for the future to then remove running actions. For this example, it would not matter if it's turned on or off, since we're not handling removal of other states and actions. Now add the follow engine. And you can also fill it up. But now we have an issue, we don't have set up the navmesh agent yet. So let's do that. Navmesh agent. And also make sure that you have a navmesh surface in your scene so that the navmesh agent can walk on it. You can check out the Unity manual and API for that. Since the navmesh agent is now set up, we can edit. By clicking the autofill button, you have a convenient way to fill it up automatically. And we don't need to filter any targets yet. We could output the companion, but it's not necessary yet. Alright. Target is registering itself. And we don't have the movement descriptor set up. We want to read from the navmesh agent. at what speed the parameter wants to move. So if we take a look at the animator controller and its parameters, we have the blend move float parameter and its blending tree to map the movement. So that's why we need to read the enough mesh agent's desired velocity to then put it into the blending tree to display the right movement animation. Also set up the enough mesh agent speed to 1. Now let's define the blackboard keys for the animator engine to write the desired movement value in, to be later read from the animation action objects that then finally set the animator controller parameters. So that should be everything. Now let's find our target and place it near to the companion. Alright, let's see what happens if we hit play, and let's also open the graph to debug it. Remember to select the decision system you want to see debugged in the graph. Without any decision system component or hosting object selected, you won't see anything in the graph editor happening in play mode. And as you can see, it follows the entity. So we have a companion that goes behind it at a specific angle, which is set up in the flank follow settings we have seen. Moving the target around will cause the companion to follow at the same spot. And you see the debugging graph displays only one decision made at start. So the tree is only traversed once and put the actions into place to the desired or respective engines which act as schedulers. This is not a very sophisticated example, but it is showcasing a quick and easy setup. Now let's take a look at the demo implementations. First one being tower defense. We have archers that need to fire from a distance or make combat from distance. Can also do melee combat or flee. Then we have paladins who want to chase the closest target to destroy it and then proceed to the next one. Also can die. Then the giant towers who are static and shooting from a safe distance. Up next the combat training setup and a Squid Game like red light green light scenario, where the slow stoppers and early runners get shot. And a hide and seek kind of game. Yeah, that's basically it for the quick glance. The presented demos are not that complicated and sophisticated compared to AAA AI, but the AI system allows you to go that far. Next, I will explain some demo AI setups. Let's take a look at the hide and seek demo example and how it is set up. First things first, if you want to keep the scene view in focus, this is a nice helper class found in the helpers dependency package. So if I press play, the game window won't be focused, but the scene view will be kept in focus, which is nice for debugging. Let's first take a look at what entities we have. We have 3 entities in this example. The hide box, which is an AI entity actually. The hider, which tries to flee and hide. And the seeker, which tries to search and chase the hiders. We can take a look at the hide spot first. Let's try to find a nice docking place for it. And we can observe what will happen So right now, as we see, it's in the unoccupied state, and now the seeker will enter it, a new decision is made, and it's in the revealed state. So basically it checks who entered this hide spot. This is the root we saw, and it plays animations based on who entered it. And how does it know which state to go into? Well, on decision made it checks the conditions, which are state conditions. So it checks if it's either in a revealed red condition or in an occupied condition, which links to its spotting system, which runs forever and does not have to be included in the decision making process. That's why it's called on enable. So it checks the spotting setting by contact and reacts to the spotted. Either it is a seeker, which we check by name, or if it's a hider, which we also check by name. And then, depending on what entity is spotted, we assign the state to itself. So we can also observe that real quick. Maybe there's a better spot to put it in. Play it. And see what state it is in. Now it's in the occupied state because the entity entered it. And the other one cannot enter this one because it's occupied. And if someone else entered, like the seeker, it is revealed. And if you look into another one, which is this one, now it's in the green state, not like this one. It's also marked as green, which is free in this case. Alright. Up next we can look at the seeker. First let's check what it does in general. It tries to chase if it's in the state chasing. And how does it know if it's in the state chasing? Well, it also has a spotting mechanic, actually two, one by contact and one by view cone. It also triggers spotting every 200-300 milliseconds and does not have a spot delay, but it can forget spotted in about 2 to 3 seconds. Same goes for contact spotting. And the reaction to spot by view cone, is it by view cone? Yes, is if the entity is a hide spot, so we check if it contains the finish tag, and if it's not in a revealed state, then it spots a hide spot to follow. And the other one by contact is the hider, also by, so it's a shared reaction to the spotting. It's reacted to view cone and contact spotting. It detects a hider it wants to chase by name, and if that's the case, these states are assigned state chase or investigating if it's a hide spot. So that's that, but there's also a priority here because we use a single decider which only applies the first valid found decider, and here we use multiple deciders to apply multiple action settings in the end. So the first priority if valid is to chase, the second one is to investigate, not revealed hide spots if it's in the investigating state, and the other one if it has not found either a hider or a hide spot, it randomly goes around and it's using this follow action to choose a random point and is restricted to a certain area. And we can take a look how the object is set up. So for the seeker we have an animator, we have a nav mesh agent, the entity which on state change makes another decision. Be careful with this setup because the bigger the complexity gets of your AI, this might also be equivalent to checking decisions every frame. So for smaller AI it's nice, but for bigger ones you should probably stick with spotting and timing the decision makings. You can do that by using something like an alarm clock mono behavior to trigger an event every second or even minutes or so. It's also found in the dependencies helper package. We have a spotting collision detector, which is used by the spotting engine of this seeker. Let's close the tab real quick. Also an animator engine to animate the movement based on the desired nav mesh agent movement speed, the follow update engine, and the spotting engine, which then sets the spotted entities to the spot descriptor. And here we also have filters. We differentiate between hiders and hide spots. And we can also see how the differentiation works by going to the decision system. And it should be in the reaction. See, it contains a filter to filter out the hide spots and hiders and which one to follow when. Here we have the filter and the follow settings on the follow engine, which then is used by the respective follow setting. And if you look at the hide spot entity, so as you can see, you can have AI that is also an object, like a tree or something like that, or whatever you want. So it's not restricted to any model or animator or rig or whatever. It's up to you. It can be a bird, a fish, a car, a lamp, whatever you want. Also we see that the entity is registering itself to a global runtime set. So we can use it in the graph editor, but you can also link the references directly if you, for example, in the follow engine, assign the targets container, destination container. This way you can also create an enclosed environment and have more flexibility reusing the AI structures. Back to the hide spot. We have an AiMalgam entity and it does not call the decision upon state change event. It also wouldn't work in this case because we do that by spotting. Here you see after spotting an entity by contact, either the seeker or the hider, the decision is made. So we use an event-driven decision-making mechanic. So we don't check or traverse the graph every frame, but once every spotting is done. And the actions get executed separately in their respective engines. So this is a huge performance boost to the traditional behavior tree or decision tree pattern, even the state machine pattern. It is a huge benefit. Alright, that's basically it for this one, although we can look at the hider real quick, but it's a similar setup to the seeker. It tries to flee, and here we also use a subgraph because we reuse the flee mechanic for the archer. And that's how the flee subgraph looks like, very simple, and you can reuse it modularly. So we remove normal walking and the land movement, or searching randomly and walking in a normal way, and assign the flee setting, which already has some stuff set up, like in which direction it should run, only in front of it, or can it flee in some other random points, can it flee behind it, but then it would run towards the chaser, stuff like that. And that's the basic setup. Also needs an animator, enough mesh agent, and here we also have an alarm clock set up to make a decision every 2 to 4 seconds. So this is the traversal, but the action execution is treated separately. Let's first go back to the hider. So we had the flee setting at first, then if it can hide, which is also dependent on what entity is spotted, either if an hide spot is spotted, that is also not occupied, so I can only enter it if it only contains itself and not any other entity, and if it's in a green state, or at least in an occupied state and not in a revealed state. So revealed state would be the red hide spot we saw. So this is hiding only if a target is spotted, and the other one is running around trying to find the next hide spot, and if it gets detected it flees then. It's a very basic setup. And we split again. The spotting runs forever, doesn't need any decision traversal because it's a core mechanic that always has to be done, and we call it on enable. You can also call it on start or awake if you want. Alright, now let's go into a more sophisticated AI behavior. Let's take a look at the Paladin. For the Paladin we have a bit more set up, although the graph is not as complex. Well, it's actually is not that easy to understand at first glance. So on the root we don't really need traversal. We only look at another target, and only if we're in the combat state. So the Paladin actually does not need lots of condition decision making. It just enables its combat, and the combat system runs separately. We have the go to combat state, so this is like a sub-branch behavior for the actions with the combat state property attachments, where we want to go to combat once it's out of reach. And this one inverts the distance, so if it's out of range, it goes to the go to combat state, and otherwise it's in the ready combat state and either blocks with a random chance, and if the other entity is not blocking and a Paladin, or it attacks and swings the sword, also only at a certain range. So how does that work? Maybe take a look at the Paladin. And this is only one of the two setups. The other one is the combat decider, or the visual part. Well, let's open up big again. Here it's a bit more. We have more like combat reaction stuff going on here. The Paladin can die and place the death animation and destroys itself afterwards in an async manner. So the destroy self waits for the death animation to finish. Well, it's actually done quite fast, but the destroy self action needs to delay for 4 seconds before it activates, and then the entity gets destroyed, which is not the case for the training combat but for the tower defense combat, since we do not have health or lethal impacts in the training scenario. Then we have impact animations, which get played if we are in the impact stage, and this one specifically plays the block animation. We set in the animator controller. We have certain impact parameters going on here. So we have actually 2 deciders for one entity, which is also fine. You can have multiple decision systems that split their work, like visual stuff and logical stuff. In this case, impact attack animations versus combat and movement decisions. Although the first one we saw isn't really a decision behavior, rather an initiator, and the second one is more reaction stuff. So let's take a look what happens in the reaction stuff. And you also see how many decisions are made, so we can count how performant and effective the traversal is. Yeah. And how do these combat state properties know what to do? Oh no, it's a bit annoying here. So, state properties. They are in ready and block and attack, and they always wait for the animation to finish. So how does the combat tool work? Note that this is the reader, by the way, for movement, mapping the desired Navmesh agent movement speed to the humanoid movement. Let's go to the combat tool. So we have the combat descriptor, which sets the impact, or which calls some impact scripts and makes the decisions, so the traversal is initiated. And we have the combat tool destination container and the combat tool itself here. So how does the combat tool work? We first subscribe from the demo tool, set up the animator descriptor to get the engine from, and set the hash values for attacking in the blackboard so we can read it from the animation action object. And once executing the combat, which is called by the combat action, we check which combat state it is in and set a random attack value, which is then put into the animator parameters, so it knows which attack hash to play. If you look at the animator and go to the combat section, you see that it checks the attack state, and this we read from the animation action. Impact or attack. Yeah, we read an external value from the blackboard and the attack, and this is the same hash. So that's how the attack animation is played and initiated by the combat state property. Then how do we know the combat is done? Well, this we do in the animation subscriber. So this is how you can create complex combat with animations. So we have the animation subscriber, which checks the combat tools, and upon receiving a finish attack event, you can apply the next combat state properties. Also on finish impact. And where are those located? If we go to the AiMalgam animation, for example here, not this one, and go to attack slash, can set up events right here. Here's one, and this method then gets called, and for that you need an animation subscriber. So we have several components working together to make the combat work with animation events and waiting for animations to finish, and then choose the next combat state property, which is similarly done for the archer drawing and shooting its bow. This is a quite more complex setup, not because the decision tree is bigger, but because we use other Unity internal procedures and other mono behaviors to work with the AI decision making and action execution. But if you are not purely working on a logic based game environment, you often have to react to other certain events and visuals to finish, to proceed with the next action. Let's have a quick look at another combat action system, which is the drone. And here it is basically a similar setup, that it does not really need decision-making traversal, but rather runs the combat action from the beginning on. But does not execute them each frame. Even the look at setting is not executed each update frame from the engine. So what do we have here? We have a simple combat state property setup. Also, we don't wait for any animation events, so if it would be instant, it would shoot like, well, how much your machine gives in a frame. But now it's like every half a second it will shoot a projectile, because it does not for the gun tool to apply the next combat state property. You can also handle it that way. And what does the gun do? Well, as we saw in the previous introduction, it shoots a projectile at the entity that does not stop quickly enough in the red light green light game. And we have the projectile combat tool here, which just shoots a bullet prefab, and the hit applier is located in the bullet prefab. So it sets the state death upon impact, which is here the runner, and we can take a look how the runner reacts to the state death. So the runner actually uses tree traversal. It should either run to the win spot or stop at a chance. So this is its room for error. It does stop on 80% chance. It's like the reaction time or stubbornness, you can argue like that. and only if it's the red light, green light, red state of the observer, and it reacts to state death, which is the second most choice. It's an async multiple decider. First the death animation will be played, then the destroy solve. And yeah, here's the condition. One state death, which is used 8 times in 8 different graphs. And once it's in this state death, the entity will, well, play the animation and vanish. You can take a look how that looks. Also, you might ask, well, if the drone, if it doesn't have any tree traversal really, how does it know when to attack and when not to attack? This is because we set up the target amount and we do not have any runtime set list, but the drone's target via engine, they target entities right here want us to follow and attack. Also does not use this one, then it must be the follow engine, and the follow engine outputs the targets. This is how it's done. We have the look at, which outputs the target, and it chooses the addition by can attack. So this is the choice it makes. Every 80 milliseconds it tries to find the target. So it's similar to spotting in a way. It already knows which targets to spot from. It's from this entity list, the raw list, and it filters out which one it can shoot. So it looks at one entity, outputs the looked at target, and the combat system that now has a valid amount of targets to shoot at. And also see how the list is filled. Here will be displayed type mismatch because it's from the scene context. There we have the arrows, and you see the projectiles getting shot. The death animation is played, they vanish, and we have a respawner kicking in, which is in the, it's not in the environment, it's here. It's a nice handy script. Right, so that's basically it for the demo showcase.